Hello guys, welcome back to Maison African Motives. Still working on our electrotechniques and for revisions. In this case, we shall be focusing on the transformers. We have got a question on transformers that we are going to consider from our November 2017 paper. So in this case, we are given that was on 6.2, where we are given the no load current of a 3,000 to 150 volt single phase transformer. So take note, the single phase transformer that we have is 25 amps at a power factor of 0.3. So we are given the power factor. The primary windings is 150 turns and the supply frequency is 60 hertz in this case. All right. So from this part, take note, we are dealing with a no load current in this case, given the voltage of 3000 S2 150, that is, we are given V1 over V2 in this case, which is 3000 volts over 150 volts. So simply, we have got the value of V1 and we also have the value of V2. That is what we simply have in this case, whereby these are measured in volts. And the no load current at that moment is given as 25 amps. So that is our no load current of 25 amps at a power factor of 0.3. So we have got the power factor of 0.3. The primary windings has got 150 turns. So we are given on the primary, N1 is equivalent to 150 turns, and the frequency is at 60 hertz in this case, and we have a frequency of 60 hertz. All right, so that is the information that we are given at no load. Then the question that we are given on the first place here was to calculate the following: the maximum value of the flux in the core, the maximum value of the flux in this case. The moment we talk of maximum value on a transformer, first thing that you're supposed to think about there is our EMF equation. From our EMF equation, we understand that we can calculate the EMF by the formula. E is equivalent to 4.44 times the frequency times the maximum flux in this case times the number of turns. So it's going to depend with what you are given. If you are given E2, if you are given V2, you must have N2. Here we are given number of turns, that's N1. So you're going to use V1 in this case. So meaning to say here it is going to be E1 and here we are going to have N1. Are we having everything? We have the frequency, we have the number of turns, we've got the EMF, which is the voltage in this case in the input, which is of 3000 volts. So all we need is to make this the subject of the formula. We are going to divide by 4.44 and the frequency and the number of turns so that we remain with the maximum flux. So divide by 4.44 times frequency times N1 both sides. We are going to remain with what? We are going to remain with the maximum flux in this case. So as we can see, this part and this part will cancel. Thus, our maximum flux is going to be the voltage over 4.44 times the frequency times the number of turns on the primary. Since we are taking the voltage from the primary, the number of turns should be from the primary. If you take from the secondary, the number of turns must be from the secondary also. So the voltage is the one that you're given from the voltage that we have V1 over V2. So that is 3000 in this case over that's 4.44 times the frequency. In this case, we've got a frequency of 60 hertz times the number of turns in the primary. In the primary, we've got 150 turns in this case. So this is going to give us the maximum flux, which is going to be 0.7. That's 0.07. 0751, something like that in webers in this case, of which we can convert this to milliwebers. It's up to you. Multiply by 10 to the exponent of 3. That's converting to milliwebers in this case. But that was the idea of our question in this case, to calculate the maximum value of the flux. Sometimes they might ask to calculate the maximum flux density. You calculate the maximum flux. After calculating that, you now calculate the maximum flux density, depending if you are given the area for that particular question. All right, on 6.22 now, they want us to calculate the power loss on no load, the power loss on no load. When you are dealing with the power loss on a no load, this is the total core loss. We are talking about the total core loss in this case. That is, we are referring to the ion losses. And as we know that the ion losses is from our true power, which is given from voltage times current times the cosine of theta in this case. But since we are working with a no load current, so meaning to say this theta is the power factor at no load. This current is the current at no load. The voltage is our input voltage. So that is when dealing with the power loss, we are talking about the total core loss or the total ion loss that is taken from the true power in this case. All right, so this one, we were going to just save our information, substitute direct. I think this one, it's direct. So like I said, our power, which is P loss, is equivalent to the voltage times current times the cosine of theta, because we're talking about the true power. So this is the power factor at no load. This is the current at no load, the input voltage in this case. So we have everything in this case. The input voltage V1, remember I said is 3000. The current there is 25. So we are going to have 3000 multiplied our no load current of 25. Cos theta represents the power factor. Whenever we are talking about cos theta, we are talking about the power factor. So we are going to substitute our power factor in this case, which is 0.3. So our power factor, that's 0.3 in this case. All right, so that is going to give us the total core loss, which is the ion loss or the loss on the at no load in this case. All right, so that was going to be 22,500 watts, which we can convert to kilowatts, divide by 1,000. We are going to obtain 22.5 kilowatts in this case. That is the one that we obtain from what? From the given core loss part. They are talking about the core loss. Remember, we also have the core loss component. If we are to draw our phasor diagram at no load, we shall see that other part I'll explain on this question here, whereby now they want us to calculate 6.21, the value of the magnetizing current, the value of the magnetizing current in this case. All right, we actually had two options that we can apply to calculate the value of the magnetizing current, which is given as IM. Remember, these are components that we simply have on our no load diagram. Remember, on our transformer no load, we have got something of this nature where we've got our diagram in this way. That is the current at no load. This one, we are going to have our current at no load in this case. This one, that is our no load current, all right? And the angle theta at no load, this is our theta, not in this case. Here we are talking about the flux. So this is going to correspond at this point. It is going to correspond to the magnetizing component and to the core component. So here, that's where we have our magnetizing component, which is given as IM. Then the core loss component, which is given as IC on this side. That is what we have. All right, so like I said, this is our core loss component, the core loss component, core loss component in this case, which is the core loss current. This is our magnetizing current in this case, which is the magnetizing component. It gives us the magnetizing current from this way. So in this case, we are given the no load current, if you still remember from our information. I want us to be careful here. We want to calculate the magnetizing current. We have the no load current of 25 amps and the power factor of 0.3. These are the two things that I want here. So we have got our no load current of 25 amps and also the power factor of 0.3. So I'm gonna work with these two. Like I said, I'm going to explain another way also. so that we can understand that it's simply one and the same thing. If we are to take note here, if we are to calculate our magnetizing component from this diagram, it means we need to find this theta, angle theta here, because we know that the magnetizing component is equal to I naught, which is the no load current, times the sine of theta in this case. So meaning to say we need the angle that is at this point. This angle that we see here is the same as the angle that is going to appear here, because these two lines, they are parallel. So this is where you have your theta naught in this case. So you are focusing with the magnetizing component, which is opposite, and you are given the no load component, which is your hypotenuse, if you are to consider your triangle here. So the ratio that was going to use the opposite and the hypotenuse at the same time was supposed to be taken from the ratio of sine of theta, where we know that the sine of theta is equal to the opposite, which is our magnetizing component, over the hypotenuse, which is the no load. So if you are to make this the subject, you are going to have Im is equal to IO sine of theta naught. That is the one that you're given, or you're just supposed to know this part or to know your formula for the magnetizing component. So as you can see, if you just understand this and you're knowing your formula, you can simply determine your magnetizing component, because what you just need is the angle theta, this one, the angle that is affecting. Where do you find the angle? From the power factor, because we understand the power factor means the cosine of theta. So meaning to say we are given the cosine of theta naught, which is a 0,3. What is going to be theta naught in this case? So that one is going to be a cos 0,3 on our calculator. So that means we are going to obtain 72,542 degrees. That's shift cos on your calculator, shift cos, you've got 0,3. So having the angle, this one, we can substitute back here to calculate our magnetizing component, which is the magnetizing current. We have the no load current there at which is given as 25 times the sine of theta, which is the sine of the angle that we obtained of 72,542 degrees. So that is going to give us the magnetizing component in this case, which is going to be 23.848 amps. All right, so that is how we could have played around with our transformer no load diagram. It has these formulas. You're supposed to know all the formulas. The formula for IC is given as IO cos of theta naught in this case. If you want to find the no load current from the this IC, this is same as IC on this part. So meaning to say our no load current is equal to the square root of IC squared plus IM squared. These are formulas that we are supposed to take into consideration. And also from the power, which is the loss, we can also talk of the loss in this case, whereby P loss is equal to, remember we said VI times cos of theta, which represent the ion loss. The same loss can be taken from VI times IC, in this case, this one, this IC, this one from our component, whereby IC is equal to I naught cos of theta. So as you can see, it's just playing around of formulas here. If you substitute IC here, which is I cos theta, we are back here because we are saying this one, I naught cos of theta, this one, that is our IC. So it means the power loss can be calculated from voltage times the current of our core loss component in this case. All right. So like I said, there are so many ways that you can play around to calculate whatever that you want to calculate. All right. If we are to take this into consideration, let's say I did not want to use this one direct. I wanted to work from this power. Remember, we were given the power in this case. We calculated the power loss in this case, and we said the power loss, if you are to consider here, this power loss, it contains of IC. So meaning to say I could have calculated the same magnetizing component in another way. So we could have taken from P loss, all right? So from P loss, which is the power loss, which is our ion loss in this case, or the core loss in this case that we have, the total core loss, we found that this formula can be given as what? As VI, that is voltage times current, V1 times the current of the component, the core component. So meaning to say we have V1, we have the power loss, we can calculate IC. So I want you to take note another way that we could have calculated. We are going to take our power loss. Remember, our power loss in this case was 22.5 kilowatts. This one, 22,500. That is our power loss. And the voltage there, V1, remember our V1, it was 3,000. That is our V1 here, which is 3,000. So I need this power, 22,500, and also that value of voltage, which is the input. So the power, remember we said is 22,500 is equal to V1. We are given V1 as 3,000 in this case, all right? So this is 3,000 times IC, which is our core loss in this case. So if we divide by 3,000 both sides, we divide by 3,000 both sides, we are going to obtain IC in this case, which was going to be 7.5 amps. All right, so if you have this in mind that I have IC, and now I want to calculate IM, this one. Remember, on our no load phasor already, we have our no load current we are given as 25 amps. So we have our no load current of 25 amps in this case. So with this, can't we calculate the magnetizing component? Because this is the one that we are supposed to calculate our IM. So from this formula that I stated here, I said the no load current is equal to the square root of IC squared plus IM squared, meaning to say we are going to use this formula this time since we are working with what? With the currents now. So we are going to have from our currents, we saw that I naught, which is the no load current, is equal to the square root of IM squared plus IC squared. So as we are supposed to calculate IM, so you can simply substitute I naught, which is 25. So that's 25 is equal to the square root of IM is the one that we are supposed to calculate plus IC in this case, which is 7.5 squared. So we're gonna square both sides. So that is how you could have calculated the same answer that we obtained. So it's gonna be IM squared plus 7.5 squared. Transpose this to the other side so that it can be a negative in this case. So that was going to be 25 squared minus 7.5 squared equal to IM squared. So in order for us to remain with IM, definitely there we're gonna introduce the square root. So that means our magnetizing current is going to be the square root of 25 squared minus 7.5 squared, which in this case was going to be 23.848 amps. So that is another way that we could have calculated, since we have the core loss, the loss of the power in this case, and that power, it consists of the core loss current. So we can use that, or we can use this option to say we can calculate this from our IC, which is from our IM, which is IM is I naught sine of theta. So this theta, we are supposed to take it now from the power factor, because we understand that the cos of theta is equal to 0.3. You find the theta arc cos on your calculator, that is shift cos. You find the angle, then you can simply calculate your magnetizing component. That is how we could have calculated it, as long as you have this understanding of your no load phasor diagram. It's not going to be that much. It's not going to be that much. You just need to know the basics there, or you can work from the power. From the power, you calculate the core loss current in this case, or the core loss component. With that component, it is the one that you're going to use back on our formula of calculating the no load current. We simply make IC the subject. If we were to make IC the subject, IM the subject, it was going to be IM is equal to the square root of I naught squared minus IC squared, which is the no load current squared minus component of core loss component squared. So that is, we could have used our formula direct as it is. Okay, just a matter of playing around with your formulas. So we shall see more questions to come as we are revising, so that we'll see how do they ask these typical questions. And we just have to be careful when dealing with transformers. The best formula to use is the one that you are supposed to work with, but any alternative way is still needed.